Hello all, welcome to Chemistry Edu Hub channel. Let us see the basicity of amines and aromatic amines in this video and what are the electronic displacements that affects the basicity of amines. So the first one is the electronegativity of the donor atom. Basicity of amines is mainly affected by the electronegativity of the donor atom. For example, if the donor atom, generally in amines, the donor atom is the nitrogen because it has one lone pair of electrons on it. Now, this is the donor atom or electron releasing group or electron releasing atom we can say. Now, if the electronegativity of this atom is increasing, that will result in the acidic behavior. If the electronegativity of the donor atom increases, that leads to more acidic behavior. So the electronegativity of the donor atom should decrease. So let us see with few examples. Suppose we have methylamine, then we have ethynylamine or vinylamine, then we have CH3C triple bond N. So the bond between carbon and hydrogen here is single bond, here it's double bond, and here it's a triple bond. So we know that single bond is less acidic compared to double and double bond is less acidic compared to triple bond. That means electronegativity is more in the case of triple bond. So the basicity order also will be in this manner. So with the increase in the electronegativity of the donor atom, the acidic behavior increases. So what happens to the basicity? Decreases. So this is the basicity order for these amines. Okay. Similarly, if we look at the aromatic examples, this is the 6-membered compound with nitrogen. Then we have another example, that is pyridine. So now here it is sp3 hybridization because there is no double bond. Here it is sp2 hybridization because all are double bonds. So sp3 hybridized nitrogen is more basic compared to sp2 hybridized nitrogen. This is because of the more electronegativity of the donor atom. So the first factor that affects the basicity of amines is the electronegativity of donor atom. The second factor that we consider is the inductive effect or plus-I effect. This is the most important factor that affects the basicity of amines. So now when the electronegativity of the nitrogen is same in all cases, then also with the effect of inductive effect on the molecule, we can observe the change in the basicity of amines. So let us look at few examples here. This is the tertiary amine. Then we have secondary amine. Then we have primary amine. How do we know which is primary, which is secondary, which is tertiary? When one hydrogen of ammonia is replaced with one R group, then it is primary. When two hydrogens are replaced, then it is secondary. When all the three hydrogens are replaced with R groups, then it is tertiary amine. Now simple NH3 is ammonia. So here we have hydrogens. We know hydrogen is a very least or very less effective plus-I group, and R groups are little more effective plus-I groups. So here there is only one plus-I group, here there are two plus-I groups, and here there are three plus-I groups. Now what is the importance of plus-I group? It adds electrons onto the nitrogen. So as more electrons are added onto the nitrogen, then when more electrons are added on to the nitrogen, definitely the electron density on nitrogen is going to increase and the basicity is going to increase. So what is the order? What is the order here? Tertiary greater than, secondary greater than, primary greater than ammonia. So though all the nitrogens are equally electronegative here, but because of the presence of different plus I groups on the nitrogen, the basicity is differing. So tertiary amine is more basic than secondary, than primary, than ammonia. Now here comes the twist. Now this order applies only in the gaseous phase of amines. When the amines are in the gaseous phase, only then we can observe this order of basicity of amines. What happens in aqueous solutions? Let us see with the example. So here is the tertiary amine and secondary amine. So naturally, since more plus I groups are there in the tertiary amine, this has to be more basic compared to the secondary amine because it has only 2 R groups. But in the aqueous solutions, there is a factor that is affecting the basicity of tertiary amine. What is it? The hydrogen bonding. There is an interference of the hydrogen bonding. So when you look at the conjugate acid, since this is a base, when you add a proton to this base, what do we get? When a proton is added onto this, we get a conjugate base, conjugate acid. Now this conjugate acid is stabilized. This conjugate acid is stable due to the hydrogen bonding in it. So whenever the conjugate acid is stable, its corresponding base is going to be less strong, or we can say weak. Let me clear it once again. In case of aqueous solutions, tertiary amines are less basic compared to that of the secondary amines. The reason behind this is whenever a base accepts a proton, it turns into conjugate acid. Now if the conjugate acid is stable for any reason, now here the reason is due to hydrogen bond, this conjugate acid is stable. Then the corresponding base is going to be weak or less strong. So because of this reason, the order is secondary amines more basic than tertiary, than primary, than ammonia. This is the reason for the different order of basicity in case of aqueous solutions. The third factor that affects the basicity of amines is the resonance. Resonance is the involvement or delocalization of the lone pair or pi electrons. So as the resonance increases, the acidity increases and the basicity decreases. So comparatively, aromatic amines are less basic compared to that of the aliphatic amines, because in case of aromatic amines we observe the R effect or resonance. So the examples are ethylamine more basic than vinylamine, more basic than phenylamine, or you can say aniline. This ring is nothing but the C6H5 ring, more basic than the CH3COCH3 acetone. So these are the examples for the comparison between the basicity of aromatic amines and aliphatic amines. We have just seen the resonance decreasing the basicity, but the exception for this is imines. So in case of imines, we observe that resonance increases the basicity. As the resonance increases, basicity also increases. So what are imines? Carbon, nitrogen, double bond containing compounds are imines. So the examples are CH3, CH3, carbon, nitrogen, double bond we see. Then we have CH3, monosubstituted imine. Then we have trisubstituted imine, disubstituted imines. NH2, carbon NH2, carbon NH. So here it's the monosubstituted, disubstituted and trisubstituted. So the first compound being less basic compared to the second compound compared to the third compound. So in case of imines, with the increase in the resonance effect, the basic nature is increasing. This is an exception for the general cases. Now let us see the basicity of aromatic amines with various examples. So as we have discussed already, aromatic amines are less basic compared to that of the aliphatic amines. So what is the main factor for basicity? Basicity is inversely proportional to that of the number of resonating structures. If there are more resonating structures, then the substance is going to be less basic. It becomes more acidic. Similarly, basicity is inversely proportional to electronegativity of nitrogen. This is a simple rule for basicity. Now let us see various examples in which the basicity of aromatic amines is better explained. So as the number of benzene rings are increased, or we can say phenyl rings are increased, the basicity will decrease. B indicates basicity. So here there is one phenyl ring with NH2. So basically this is aniline. Then we have two phenyl rings connected to nitrogen. Then there is three phenyl rings connected to nitrogen. So as the number of phenyl rings or benzene rings increases, the basicity will decrease. Obviously, this is the order. Similarly, on the benzene ring, on the aniline ring, if the alkyl groups are increasing, suppose if this is the aniline, if the hydrogen is replaced with methyl, then because of the plus I effect or increase in the alkyl groups, obviously this will be more basic. These are the few examples. Now what's happening here? Because of the more bulky methyl group being on the nitrogen or around the nitrogen, there's a steric hindrance. Let us see one more example. Nitrogen with two methyl groups. So what happens? The delocalization is hindered of this lone pair because of the more bulky groups or methyl groups attached to the nitrogen around the phenyl ring. So hence, aniline is less basic than the monosubstituted than the disubstituted. This way, basicity of aromatic amines is also affected. Orthosubstituted anilines are less basic compared to that of the rest of the substituted amines. It's because of the ortho effect. We have seen ortho effect already. You can go to that video and check it if you haven't followed yet. Okay, so the order will be 4, that is para greater than, meta greater than, simple aniline greater than the ortho. Ortho is least basic because of the ortho effect present at the ortho position. Ortho substituted amines are less basic compared to that of the para and meta substituted amines. Let us see the most important factor that affects the basicity of aromatic amines, that is the steric factor. Now what is the steric factor? Stereo is nothing but the arrangement of groups in the space. So when they are arranged in the space, how they are going to behave? if the space is available or not, if there is any hindrance to their movement, that is nothing but the steric factor. So let us see amine with substituted nitro groups at 3rd, 4th and 5th positions, and the aniline with 2 NO2 groups and 1 cyano group. So compared to cyano group, nitro group is more electronegative. NO2 is more electronegative compared to cyano. So in such case, what do we observe? Definitely 2 should be more basic compared to that of the 1. But because of the steric factor, 1 is more basic compared to that of 2. It's because there are 3 nitro groups which are bulky. Because of the congestion in the space available for these nitro groups to move, the effective electronegativity is not shown by the middle nitro. But here there are 2 nitro on either side and there is a small cyano group. Cyano group is also the group that has high electronegativity but not as high as NO2. So cyano is going to show its effect at the para position, and accordingly that will decrease the basicity, and hence the first compound is more basic compared to that of the second compound. Now the factor here is the steric factor or steric hindrance. Similarly, look at this example where aniline has NO2 at para positions in both the compounds, para nitro aniline, but with methyl groups on different positions. In the first compound it is at both the methyls are at ortho position, and here both the methyls are at meta positions. So we observe the first compound being less basic than the second compound. It's because due to the 2 bulky groups present in between the nitro, it is hindering or affecting the electronegativity of nitro group. But here the methyl groups are at ortho position and this group is free to show its electronegativity and increases the acidic behavior. So hence the first compound is less basic compared to that of the second compound. Let us see the basicity of amines with 2 more examples. That is the first compound with aliphatic amine with the cyclic ring, and the second compound is the bridge compound. Now here the second compound is more basic compared to that of the first compound. It's because in the first compound the lone pair on nitrogen is free. Now since it is free to delocalize, it can easily move from here to here and here to here and shows resonance, and hence the acidic behavior is increasing. But in the case of second compound, what do we observe? The lone pair is attached to the bridge carbon. So the lone pair, if it is transferred here, then we observe a double bond in the bridge head. So we observe a double bond in the bridge head. This is against the Brett rule. What is Brett rule? There should not be a double bond in the bridge head. If this is the bridge head, there cannot be a double bond attached to that carbon. It's because in the bridge compounds, unless and until the rings, bicyclo or tricyclo or polycyclic rings, the ring size is sufficiently large. Here the ring size is only 4. So in such case, the compound becomes very much unstable. So then we cannot have a double bond attached to that bridge head carbon. So since this is against to the Brett's rule, there is no delocalization in the second molecule. So hence, first one is less basic compared to that of the second compound. So these are few examples about the acidity to explain the basicity of amines and aromatic amines. Hope you liked the video. Thank you for watching. Please do like, share and subscribe. Thank you.
Hello all, welcome to Chemistry Edu Hub channel. Today we are going to discuss the acidic nature of phenols, which is the most important concept. So let us see what are phenols first. Phenol is nothing but the phenyl ring or the benzene ring. When we replace one of the hydrogens with OH, we are going to get the structure of phenol. Simply, this is considered to be an aromatic alcohol. Benzene ring with OH group is an aromatic alcohol, which is generally called phenol. Now, the acidic nature of phenol, if we are going to discuss, we need to look at the stability of its phenoxide ion. Stability of the phenoxide ion. Now, what is phenoxide ion? Whenever from the phenol, if we remove the proton means hydrogen without any electrons, just the H plus if we remove, the bonded pair will shift on to the oxygen, and that will result in the formation of phenoxide ion. This is the structure of phenoxide ion. So based on the stability of this ion, we decide the acidic nature of phenols. Suppose if there is an electron withdrawing group. Electron withdrawing group is something which will pull the electrons from O minus. That will stabilize the phenoxide ion by reducing the negative charge on the phenoxide ion, and the stability increases. Now that will result in the more acidic nature of phenoxide ion and the phenol. So acidic nature also increases. Similarly, if there is an electron releasing group, suppose if there is an electron releasing group, already there is negative charge on the phenoxide ion. Here, if the electron releasing group is still adding electrons onto the phenoxide, so ultimately the stability is going to decrease. When it is less stable, the acidic nature also will decrease. These are the two main factors that will explain the stability of phenoxide ion and also the acidic nature. Now let us see the acidic nature of phenols with few examples. Consider few examples like simple phenol, then we have phenol with NO2 in the para position, and we have phenol with methyl in the para position. Now this is simple phenol with no other groups. This is para nitrophenol. Para is nothing but the 1,4 position. If this is your first carbon, 1, 2, 3, 4. So 1,4 position is considered to be para. Para nitro, this is para cresol. Okay, so since there is hydrogen in the para position, we consider the minus I effect or minus plus I effect of hydrogen, which is least. But if you consider NO2, NO2 is a strong electron withdrawing group, whereas methyl is an electron releasing group. So the stability will follow the order like 2. Second is more stable compared to, otherwise I'll give the directly positions. So this is first most stable, this is second most stable, and this is the third most stable, because electron withdrawing group is going to increase the stability, hydrogen is neutral, and electron releasing group will destabilize the phenol. So this way we observe the electron withdrawing group increasing the acidic nature of phenol and electron releasing group decreasing the acidic nature of phenols. Let us see the acidic nature of phenols with same electron withdrawing group. We have phenol, we have orthonitrophenol, that is at 1,2 position. Then we have metanitrophenol. Then we have paranitrophenol. So since in the first molecule there is no electron withdrawing group, this will be least acidic. Now NO2 being the minus R group, its effect is greater at ortho and para positions. So accordingly the second and fourth molecule should have equal acidic nature, but orthonitrophenol is less acidic compared to paranitrophenol. Orthonitrophenol is less acidic compared to that of the paranitrophenol. This is because para effect is greater, and also in the case of orthonitro there is intramolecular hydrogen bonding between the nitrogen of nitro and the hydrogen of OH. Accordingly there is intramolecular hydrogen bonding, and the tendency to lose proton is decreased because of this extra stability gained by intramolecular hydrogen bonding and this chelation or the ring formation. Due to the ring formation, the tendency to lose proton is decreasing. Accordingly the acidic nature decreases. So phenol less than metaphenol, metanitro, electron withdrawing behavior at meta position is least. So first least acidic is phenol, second least is metanitrophenol, third least is orthonitrophenol, and the top position is given to paranitrophenol. Or else I'll give the positions this way. So the order of acidic nature is paranitrophenol takes the first position, then comes the orthonitrophenol, then comes the metanitrophenol, in the least position there is phenol. So this way, though the same electron withdrawing group is present at ortho and para, because of the intramolecular hydrogen bonding, the tendency to lose the proton is decreasing, and accordingly the acidic nature is decreasing. Let us see one electron releasing group example also. So there's phenol, there's orthocresol, this is ortho, then there is metacresol, this is meta, and there is paracresol. Now CH3 is an electron releasing group at all the positions. Now I'll give numbering like this: 1, 2, 3, 4. So either the plus R or minus R effect, or plus I or minus I effect, it is greater at ortho and para positions and least at meta position. So accordingly, now the electron releasing group is destabilizing the phenoxide ion, so such effect is less at meta position, and obviously when there is no group the effect is even more better. So 1 is more acidic compared to 3 because at meta position the electron releasing effect is less. Then comes the para position, then comes the ortho position. So this is the order of acidic nature given in the case of phenol with an electron releasing group. Now let us see the acidic nature of acids or carboxylic acids. Carboxylic acids are those with RCOOH functional group. R is an alkyl group, COOH is the main functional group of acids. So acids are generally acidic, this is very common. This acidic nature of acids, not all acids are of equal acidic strength. Their strength also will differ according to the stability of the carboxylate ion. Just like we have seen in the case of phenol, here also based on the stability of carboxylate ion. What is carboxylate ion? It is RCOO minus. This is nothing but the carboxylate ion. So based on its stability, the acidic nature will vary. Most of the carboxylic acids and sulfonic acids are more acidic compared to that of the carbonic acid, that is H2CO3. Accordingly, whenever these carboxylic acids and sulfonic acids are added to mild base, that is baking soda, we observe the immediate reaction, and that can be seen in the form of white effervescence formed in the solution. So most of the carboxylic acids and sulfonic acids are more acidic. Now, what will increase the acidic nature of these acids? The electron withdrawing group. Whenever there is an electron withdrawing group added to the carboxylic acid, that we see increasing the acidic behavior. Electron withdrawing group is nothing but -I group. So it is going to stabilize the carboxylate ion, that is CO minus, and it will increase the acidic behavior. So let us see few examples here. So if we look at simply the acetic acid, we know acetic acid is a weak acid, that is vinegar that we use every day. Then suppose if one of the hydrogens is replaced with an electron withdrawing group like chlorine, then the acidic nature is going to be increased. Suppose if the other hydrogen is also removed, CH, Cl, Cl, COOH, then the acidic nature is even more increased. Then if the third hydrogen is also replaced with chlorine only, trichloroacetic acid is even more acidic. So as the electron withdrawing groups increase in the acid, the acidic nature also will increase. So -I effect is directly proportional to the acidic behavior of the acid. Let us see the acidic nature in the cyclic compounds also with one more example. This is cyclopentanoic acid with nitro very close to the acid. Then there is acid and nitro is at ortho position. Then there is acid with nitro at third position. Now as the electron withdrawing group move away from the acid, the effect will diminish. So first compound is more acidic compared to second, and second is more acidic compared to third. So as the acidic nature acidic strength decreases, like the effect of NO2 goes down because of the distance, the acidic nature also will go down. Similarly, formic acid is more acidic than the other monocarboxylic acids. Like if you consider, formic acid takes the first position, then comes the acetic acid, then comes the propanoic acid, then comes the more substituted acids like. So what is the reason behind this? It's just the +I effect. Methyl group that is added on to the acid is nothing but the +I groups. +I groups will increase the electron density, so accordingly the acidic nature decreases. So +I group is inversely proportional to the acidic behavior of carboxylic acids. Now these organic acids are generally less acidic compared to that of the inorganic acids. Now among the organic acids also we have aliphatic and aromatic. So compared to aliphatic, aromatic are more acidic. So aromatic acids are more acidic compared to that of the aliphatic acids. So if we look at but the exception is formic acid. Formic acid being aliphatic also it is more acidic. So formic acid being more acidic compared to benzoic acid, compared to the normal, alkyl or aliphatic acetic acid or aliphatic carboxylic acid. So this is the general information regarding the acidic nature of phenols and carboxylic acids with various examples. If you find this video helpful, please like, share and subscribe. Thank you. Hello all, welcome to Chemistry Edu Hub. Today's topic is aromaticity. This is the most important concept or the phenomenon exhibited by organic compounds. So generally when we say aroma, it is nothing but the smell. But here, okay, aromatic compounds can have the smell, but it is not wholly about the smell. It is about a property where the compounds exhibit compounds that have high degree of unsaturation, and they behave like saturated compounds. So what is aromaticity? It is a property where the compounds with high degree of unsaturation behave like saturated compounds. Such compounds, what do we call them? We call them aromatic compounds, and the phenomenon is called aromaticity. Okay, now benzene is considered to be the parent member of all these aromatic compounds. Now, what is the meaning of high degree of unsaturation? Unsaturation is nothing but the presence of double or triple bond. So when do we have a double or triple bond? Whenever there are less number of hydrogens compared to the carbon atoms in that compound. So high degree of unsaturation is also nothing but the index of hydrogen deficiency. The index of hydrogen deficiency, which also means that the total number of rings and pi bonds present in a molecule. So generally those compounds which have more number of rings in them or more pi bonds in them will show this aromatic behavior. That is the meaning of high degree of unsaturation and index of hydrogen deficiency. Now, how do these high degree of unsaturated compounds behave like saturated compounds? The main property here is nothing but the resonance. What is it? The shift of pi electrons or the delocalization of pi electrons. So, though they have more number of pi bonds, because of the resonance process, they behave like saturated compounds, and this will provide the molecules the stability that they need and the type of reactivity that they are showing. Such property is called aromaticity in the organic compounds. We need to know the conditions for aromaticity, because not every organic compound that has carbon and hydrogen in it can be aromatic. Now we need to look at the conditions for it only to identify which compound is aromatic and which is not. So the first and foremost condition is the compound has to be cyclic, it has to be planar or nearly planar. The first and foremost condition is the compound has to be cyclic. Cyclic is nothing but closed chain or ring like this. So instead of open chain compounds like this, we should have a closed ring. Such compounds are cyclic. And what do you mean by planar? Planar is either the hybridization has to be sp2, or you can identify it as like when all the atoms in the compound are on the same plane, then you call it planar compounds. So the first and foremost condition is it has to be cyclic and planar. Then each atom in the ring, whenever you have a ring, here if you consider all the carbons are sp3, Though the ring is cyclic, carbons are surrounded by all single bonds. When a carbon is surrounded by all single bonds, the hybridization is going to be sp3. sp3 hybridization will lead to tetrahedral, a three-dimensional structure but not planar form. So what is the second condition? Once it is cyclic, it has to be, each atom in the ring must be sp2 hybridized. When can be the carbon in the ring will be sp2 hybridized? Whenever there are pi electrons in the ring. So consider benzene molecule where it is cyclic and also it has alternate pi electrons, where each carbon in benzene ring is sp2 hybridized. Such molecule is said to be planar with sp2 hybridization and pi electrons. And how this pi bond is formed? It is formed by the unhybridized p orbital. What do you mean by unhybridized p orbital? The p orbital in carbon is not involved in hybridization. It is left free to form pi bond through sideways overlapping. That is nothing but the unhybridized p orbital. Now in this ring, each atom is sp2 and it is formed by unhybridized p orbital, which is allowed for the delocalization of pi electrons. What do you mean by delocalization? They keep on moving. They move from one atom to the other this way. This is known as the delocalization. Now the third condition is delocalization of pi electron cloud should have 4n plus 2 pi electrons. 4n plus 2 pi electrons. This rule is nothing but the Huckel's rule. Huckel is the scientist who gave the structure for benzene and he only proposed the aromaticity property. So inside the benzene ring or inside any ring, the number of pi electrons has to be, the number has to be equal to 4n plus 2. N is not number of pi bonds here, it is just a integer or it's just a number. So 4, if the n value is equal to 0, so what do we write? 4 into 0 plus 2 equal to 2. If the n value is equal to 1, then 4 into 1 plus 2 is equal to 6. If the n value is 2, then 4 into 2 plus 2 equal to 10. Likewise, based on the n value, we are going to get the 4n plus 2 values equal to 2, 6, 10, 14, 18, etc. So, whichever ring with pi electrons has the value equal to 4n plus 2 pi electrons, such compounds are said to be aromatic compounds. Only those compounds which have the pi electron number equal to 2, 6, 10, 14, 18, etc. so on, such compounds are aromatic. I am repeating once again, this n value is not the number of pi bonds, it is just a number 0, 1, 2, 3 so on. Okay, so this is the third condition. So these are the three conditions. The first is it has to be cyclic and planar, then second is it should be sp2, and the third criteria is pi electrons has to be 4n plus 2 inside the ring. So these all conditions make the compound aromatic. So aromaticity, what it does, it increases the stability of the molecule. Aromaticity is directly proportional to the stability of the molecule. Suppose if a compound satisfies all the 1, 2, 3 conditions but has no 4n plus 2 pi electrons, it has only 4n pi electrons, where the number is equal to 4, 8, 12, 16 so on. If the number of pi electrons inside the ring is equal to 4, 8, 12, 16 and so on, instead of 2, 6, 10, 14, such compounds are called anti-aromatic compounds. Aromatic compounds are very stable, anti-aromatic compounds are unstable. Okay, so if the compound fulfills all the above conditions but has only 4 and 5 electrons in them, such compounds are said to be anti-aromatic compounds. Now anti-aromatic compounds are unstable and they have paramagnetic behavior. What is paramagnetic behavior? They get attracted to the magnet in a large extent. So they show paramagnetic behavior. So if we look at the order of stability among these compounds, order of stability follows. As we know, aromatic compounds are the most stable compounds. Then comes non-aromatic. The compounds which are not aromatic at all are next stable. Then comes the least stable compounds. These are anti-aromatic compounds. So aromaticity brings the stability in the molecules. Anti-aromatic compounds become unstable and non-aromatic are more stable compared to anti-aromatic compounds. Let us see few examples for the aromatic compounds. So we have seen the conditions already. The first and foremost best example for aromatic compounds is the benzene. Then we have 2-ring compounds, that is naphthalene with alternate pi bonds. Then we have 3-ring compounds, that is anthracene. These are the most common aromatic compounds with the cyclic rings and planar nature. Okay, so this is benzene, this is naphthalene, and this is anthracene. Then we have hetero compounds also that show aromatic behavior. Hetero compounds in the sense, apart from carbon and hydrogen, there could be other hetero atom like nitrogen or oxygen or sulfur. Okay, so let us see examples of them. So pyridine is an hetero compound that has aromatic behavior. Then there is oxygen in the ring, that is furan. This is furan, this is pyridine. Then sulfur heteroatom in the ring, that is thiophene. Wherever there is sulfur, we use the term thio. So this is thiophene. Then we have benzofuran, indole, imidazole, pyrazole, etc. There are many different aromatic compounds. Now there could be ionic species also that behave like aromatic compounds. What are those ionic species? The 5-membered ring with a negative charge. So here if you consider, this single pi bond indicates 2 electrons, this indicates 2 electrons, and the negative charge also indicates 2 electrons. So hence overall in the ring there are 6 electrons. This follows the Huckel rule. Similarly, there could be 4 carbons in the ring with 2 negative charges. This also indicates 6 electrons inside the ring, which undergoes delocalization. So there could be 7-membered also, 1, 2, 3, 4, 5, 6, 7 with a positive charge and alternate pi electrons. Positive charge indicates no electrons, so obviously this has 6 electrons. Such ionic species also can be aromatic. Annulenes are another example for aromatic compounds. These annulenes are nothing but they are carbocyclic. That means they shall have only carbon and hydrogen in the ring, and they are monocyclic. Monocyclic in the sense, how many ever carbons are there, they form only one single ring. Such compounds are called annulenes. Suppose if you look at 4-membered ring with a alternate pi electrons, such compound is called 4-annulene. We need to look at the number of carbons. So 1, 2, 3, 4, it forms 4-annulene. Similarly, there is 6-annulene, that is benzene. So 6 we write it in square brackets, or we call it parenthesis, and we write it as 6-annulene. So the other name for benzene is 6-annulene. Then we have 14-annulene. that is this way. These are a bit complicated structures with alternate pi electrons. So this is considered to be the 14 annulene. So this has completely carbon and hydrogen in it, and this whole thing is considered to be the single ring. So hence it is called 14 annulene. Then we have 18 annulene like this. But the exception in this is 10 annulene. 10 annulene, except for 10 annulene, rest are all are aromatic, but 10 annulene is anti-aromatic. It's because of its structural arrangement. Let us see that. 10 annulene is written this way, where you will have alternate pi electrons like this, but because of the arrangement of hydrogens in this ring in the opposite direction, this molecule is becoming non-planar. This molecule is becoming non-planar, and hence the molecule is non-aromatic. Rest all annulines are planar and aromatic, except for 10 annulene because it is non-planar due to the repulsion between the two hydrogen atoms. Because of the trans arrangement, there is a strain in the molecule and these two get repelled. Because of that, the molecule is becoming non-planar and it is non-aromatic, but the rest all are aromatic in the nature. Let us see few examples for anti-aromatic also. So whichever has 4 and pi electrons in them will behave like anti-aromatic compounds. So this is the cyclic ring with 4 carbons and alternate pi electrons. So this has 2 pi bonds, which is equal to 4 pi electrons. There could be ionic species also in the anti-aromatic compounds with 3-membered ring, 1 pi bond and 1 negative charge. So this also indicates 4 electrons in it. And then we have a 5-membered ring with 2 pi bonds alternately and the positive charge. So this also is equal to 4 pi electrons inside the benzene ring. And here you have a heteroatom, that is boron. Boron is an electron deficient species. It has no lone pair. So only these 2 pi electrons will be involved in the delocalization. So it leads to anti-aromatic behavior. So this is the complete video related to aromaticity and the type of compounds. Thank you. Hello all, welcome to the Chemistry Edu Hub channel. I'm going to create chemistry videos from grade 8 to 12 of state board and CBSE and IIT syllabus and NEET, which is useful for all competitive exams. So do check out the remaining videos in my channel and follow for more updates. And in today's video, let us start reaction intermediates. So we are now dealing with the organic chemistry basics, so in which we talk about reaction intermediates. So generally most of the organic reactions are multi-step reactions. If you see in case of inorganic chemistry, the reaction happens in a single step. Reactants convert into products, that's it. But in case of organic chemistry, the reaction takes place in more than one step. So they are complex reactions. So in such case, in any of the steps, we get intermediates. Now what are these intermediates? Which have a very short span of life and they convert into the products. So reactant convert into some intermediate and then it converts into products. So such substances are called intermediates. We have many intermediates in the organic chemistry like carbocation, carbanion, carbon free radical, carbenes, benzene, etc. So we are going to deal with each and every intermediate clearly and how it is formed, what is its structure, how it is stabilized, everything. The first intermediate is carbocation. So carbon containing species could be a methyl or tri-substituted, di-substituted, ethyl, any carbon compound which contains positive charge is considered to be carbocation. This is a methyl carbocation. If at all around the carbon there are 3 R groups, then its arrangement is going to be somewhat this way. So carbon with 3 R groups and positive charge is said to be a carbocation. So this is the most common intermediate that we see in many of the reactions. Now since there is positive charge on the carbon's valency is generally 4, but here it is only 3. That means there are, instead of 8 electrons, there are only 6 electrons. So we consider it as electron deficient species, or since it is electron deficient, it will be always ready to take up electrons. So it is considered as electrophile, which means electron loving or electron liking. So carbocation is an electron deficient species and electrophile. So generally carbocation has no lone pair of electron. Of course, as it is electron deficient, it has no lone pair on it. And we see the carbon is surrounded by 3 bonds with no lone pair. So whenever carbon has only 3 bonds, its hybridization is going to be sp2 hybridization. When there is sp2 hybridization for carbocation, its structure is going to be planar and the bond angle is going to be 120 degrees. And the arrangement will be generally this way. And the orbital with electrons with positive charge. So this is the general representation or orbital picture for a carbocation. There is a vacant p orbital. Since it is sp2, carbon has 4 valence electrons, 4 orbitals in the valence shell. So only 3 are used. Remaining 1 p orbital is unhybridized and it is vacant. It is not involving in hybridization and it is vacant. So this is the structure of carbocation and its description. Now let us see what are the reactions in which carbocation can be formed. Now let us see 1 or 2 examples where the carbocation can be formed in the reaction. So first is the solvolysis of CX bond. Solvolysis is nothing but by using a solvent we break the bond between carbon and hydrogen. So whenever carbon cannot be directly taken as carbon, we take R group. So our X bond is broken by using some solvent. It need not be always water, it could be any organic solvent. So when this is broken, we get R plus and X minus. This bond is broken and we get R plus and X minus because generally X is electronegative and R is electropositive. So definitely X gets the negative charge and R gets the positive charge. Now this is considered to be your carbocation. This is one general example where we could see the generation of carbocation. And if we look at the protonation of alcohol means addition of proton to alcohol. So we take ROH as alcohol, then we add H plus. So what is H plus? Electron deficient species. Obviously OH has 2 lone pairs. What it will do? It will donate lone pair to the H plus. So obviously we are going to get OH2 plus. Now this is unstable, so it results in the formation of R plus plus H2O. Now this is your carbocation. This way carbocations are generated. Now this carbocation will not stay for a long time. This is going to combine with some other nucleophile and turn into the product. So these are the few examples where we can see the carbocation formation. Now let us see what factors are going to stabilize the carbocation. First is the less electronegativity of carbon. Now what is this? Suppose if the electronegativity on the carbon is less, for example there is methyl attached to CH2. Now this is said to be more stable compared to the vinyl carbocation. This is said to be more stable compared to triple bond containing carbocation, because as the double and triple bonds are formed, the electronegativity is going to increase, acidic behavior is going to increase. So that means simply the carbon has to be sp hybridization instead of sp3 hybridization instead of sp2 and sp. Then the electronegativity of the carbon is going to be less and the carbocation will become stable. And the second factor is the plus I effect. Plus I effect is nothing but electron releasing group present on the carbon. So whenever there is electron releasing group, that will stabilize the carbocation by donating electrons. So obviously methyl carbocation is less stable compared to primary, compared to secondary and compared to tertiary carbocation, because of the more number of plus I groups on methyl, then ethyl, then secondary and tertiary carbocations. Similarly, hyperconjugation and resonance. Hyperconjugation and resonance are going to support the carbocation stability. So if you look at resonance example, so adjacent to the carbocation, if there is a pi bond, then this will result in the compensation of the positive charge of the carbocation, and it becomes more stable compared to the carbocation with no pi electrons in the adjacent carbon. So this way resonance and hyperconjugation are going to help the carbocation stability. So this is the complete information about carbocations. The second intermediate is carbanion. This is nothing but the carbon with negative charge. So the same way as exactly opposite features we are going to see in the case of carbanions to that of the carbocations. So carbanion is formed by the removal of one atom or group from the carbon. Suppose if there are 4 groups like this around the carbon, if one group or atom is removed without removing the bonds, then what happens? This is gone as H plus and the bonded electrons will shift onto the carbon. Now this results in the formation of what? Carbanion, carbon with negative charge. So carbanion is having 3 bonded pair of electrons and 1 lone pair, or you can say unshared pair of electrons. These are 3 paired electrons and 1 is unpaired electron. So accordingly it will show sp3 hybridization. Carbanion is sp3 hybridized and it is surrounded by how many electrons? 8 electrons. So it is not electron deficient. So generally this carbanion is going to be arranged in the form of pyramidal shape instead of tetrahedral. Whenever there is sp3 it has to be tetrahedral, but here it is pyramidal geometry. It's because carbon and hydrogen's electronegativity is not very different, the difference is not very high. In such case the repulsions are not going to be that high. Because of that the arrangement is pyramidal instead of tetrahedral. Okay, this is about the carbanion and its structure and arrangement, orbital structure also. Now let us see what are the factors that are going to stabilize the carbanion. Exactly reverse of that of the carbocation, we observe the factors. What are those? One is more electronegativity of carbon. The other is minus I effect, that is electron withdrawing groups should be present on the carbon. Then earlier we said hyperconjugation, but now here it is reverse hyperconjugation. So if you have doubt about what is reverse hyperconjugation, there is a video on reverse hyperconjugation, you can go check that out. So reverse hyperconjugation supports the carbanion stability. Then comes the minus R effect. Since carbanion is electron rich, all the factors or all the phenomenon where the electron withdrawing is present, that will support the carbanion stability. So accordingly we can see, if it is ethylene, if it is ethyl, it will have least stability. Then if it is ethinyl, then it will have more stability compared to ethynyl carbanion. So exactly reverse to that of the carbocation we observe. So ethyl carbanion is less stable than ethinyl than ethinyl carbanion. So, and if you consider the simple carbanions also, here the order is reverse. Methyl carbanion is more stable than primary, than secondary, than tertiary. So this is the stability order and the factors that stabilize the carbanion in the reactions. The third intermediate is free radicals. Free radicals are nothing but the carbon species or any species which have odd electron on them. Now here we are dealing with organic chemistry, so we consider only the carbon free radicals. Now how a free radical is formed? Whenever there is a bond between two atoms, bond indicates two electrons. When these two electrons are equally distributed, I put a different arrow here instead of complete arrow. It is a half-headed arrow. We call it as fish hook arrow. We use it only when the free radicals are formed. Okay, so that means the bond that has two electrons is equally distributed among the two atoms. That results in the formation of free radicals with odd electrons. Okay, so now this free radical can be either planar with sp2 hybridization. The possibilities are two. Either it could be planar with sp2 hybridization, or it could be neither planar nor tetrahedral. Neither planar nor tetrahedral, and exist in the form of equilibrium form as a hybrid between p and sp3. I'll show the orbital structure also. So planar form is going to be this way with R dash dash, three different, this R dash dash dash, this indicates different alkyl groups, and there's an orbital with odd electrons. Okay, this is the planar form of an free radical, or it could be neither planar nor tetrahedral. Indicates what? It is either pyramidal this way, or this way. It always stays in the dynamic equilibrium, which moves continuously from one form to the other. So free radicals are expected to be either in the planar form or in this form, but we cannot say exactly which form is certainly exist in the reaction intermediate, but mostly we expect the free radical to be in the planar form only, in the sp2 form, where we see the odd electron in the sp2 hybridized carbon and also an odd electron in the p orbital. So this gives you the slightly pyramid shape, or we can say planar shape. This is the free radical orbital structure, and generally we observe free radical formation in the photochemical or thermal reactions, where the amount of energy that we supply is going to be very high. In such case, we observe the equal sharing of electrons, that is called as homolysis. Equal breakage of the bond between the two atoms that results in the formation of odd electron species. This is considered to be the formation of the structure and the orbital formation of free radical. Let us see one example. You can consider methane with chlorine. So generally the free radical formation takes place in three different steps: chain initiation, propagation and termination, where you can see the formation of methyl radical and chlorine radical, and then methyl radical again combines with chlorine radical again combines with methane. Likewise the chain propagates and ultimately methyl radical and chlorine radical combines to give methyl chloride. Likewise the reaction continues. So such homolytic reactions will generate the free radicals. Now what are the factors that will support the free radical or stabilize the free radicals in the organic reaction? Is the first thing is hyperconjugation. First phenomenon is hyperconjugation and the second phenomenon is resonance. Now these two are going to be supporting the stability of free radicals. So if you look at methyl free radical, this is less stable compared to ethyl, less stable compared to secondary, less stable compared to tertiary. Now here we have 3 alpha carbons with 9 hydrogens, 2 alpha carbons with 6 hydrogens, 1 alpha carbon with 3 hydrogens and no alpha carbon with 0 hydrogens. So this way hyperconjugation is supporting the stability of free radical. Similarly, resonance is going to stabilize the allyl and benzyl free radicals. What is an allyl free radical? Whenever there is a double bond, ethylene, one of the hydrogens, if it is replaced with methyl, now this is considered to be allyl. Double bond attached to some group, such arrangement is called allyl. Now this is stabilized by the resonance, because this will shift here and you can see the free radical moving from this carbon to this carbon. So this way resonance will stabilize the allyl free radicals. Similarly, benzyl group is nothing but benzene with CH2 instead of CH3 with a free radical. Now this is considered to be benzyl free radical. So we observe this pi electron moving this way. So accordingly this again shifts here, this again shifts here. Likewise you see the resonance stabilizing the benzyl free radical. So this is about complete information about the free radicals. The next or the fourth intermediate is nothing but carbene. Carbenes are considered to be neutral. That means they have no charge. They are neutral with no charge, and they are divalent. That means they are bonded to 2 other groups at a time, and in which these carbenes are those in which we see the carbon is bonded to 2 atoms, let's say RR or RR dash, and has 2 non-bonding orbitals that contain 2 electrons in them. Now this carbene can have 2 different kind of arrangements, and we call them either singlet or triplet. So when do we call them singlet and when do we call them triplet? So suppose the arrangement is same. This is considered to be a singlet, whereas instead of paired electrons, if there are two electrons with the same spin, in case of singlet, the paired electrons are having opposite spin. In case of triplet, the paired electrons are the electrons are not paired, and both are with the same spin. Such kind of arrangement is said to be singlet and triplet. So carbenes are expected to be in either singlet form or in the doublet form. Now if we look at the structural arrangement of singlet and triplet carbene, singlet carbene is having sp2 hybridization, where out of 3 hybrid orbitals, 2 are utilized by the bonding atoms, 1 is utilized by the shared pair of electron, that is unshared, like the lone pair of electron, and this is the unhybridized p orbital that is left vacant. And now this is going to be very close to the structure of that of the carbocation, whereas the triplet form, if we consider, the triplet form is sp hybridized. The triplet form is sp hybridized, and it is either linear or nearly linear species. It is linear or nearly linear species. Now these are the two types of carbenes: singlet with a pair of electrons, triplet with parallel spins, or the two electrons are having the same spin. We call them parallel spin. These are the two forms. And if we consider the energy of singlet and triplet carbenes, initially we consider that whichever has paired electrons, that will have the lesser energy, but according to the studies, triplet form is having lower energy compared to that of the singlet form. It is because to overcome the repulsions between the electrons and to get paired, the energy required is higher. So singlet form is of higher energy and triplet form is of lower energy. So this is the basic information about carbenes, and their stability is generally supported by the resonance. Resonance will stabilize the stability of the will support the stability of the carbenes. If we look at the decreasing order of the stability of different singlets, it is CF2 greater than CCl2 greater than. We are looking this order only in the singlets with different halogens. These are the different singlets. So fluorine has more stability compared to chlorine, compared to bromine. So the most common reason that we can give is the electronegativity. So fluorine being more electronegative, it's more stable compared to chlorine and bromine. So this is the information about carbene. The fifth and the last intermediate is benzene. So benzene comes under the category called arynes. Benzenes are generally categorized under arynes. Now what is an aryne? Aryne is an aromatic compound. Aryne is an aromatic compound that has a triple bond. So we have already seen what is an aromatic compound. It should be cyclic with pi electrons. So in the cyclic ring with pi electrons, generally we observe only double bonds. But here in case of benzene, there is a triple bond. Such compounds are considered to be arynes, and the best example for aryne is benzene. Okay, so it's generally like inside the ring we have an acetylene, it's like that. Or if we look at a benzene ring and there is one hydrogen here, suppose if we remove these two hydrogens, what are we going to get? We get a triple bond over here. Such similar structure is of benzene. So what is the other name for benzene? It is dihydrobenzene. When you remove two hydrogens from benzene, we can expect the formation of benzene. So what are all the names that benzene has? Benzene comes under the class arynes. It is also called dihydrobenzene. Now the triple bond in the benzene, it is not formed simply by the overlapping of unhybridized p orbitals, just we observe in the case of acetylene. It's not like that, because it's not possible in the case of aromatic compounds. It is formed by the overlapping of the orbitals of neighboring carbon atoms. If we look at the benzene structure, so here the carbon has p orbital, here also the carbon has p orbital, then we observe the overlapping this way. Now this results in the formation of the third bond, that is the triple bond. Okay, so such arrangement leads to orthogonal form inside the benzene ring. This way a triple bond is generated in the benzene, unlike in the case of acetylene where the sp hybridization is possible. Okay, let us see a few examples where the benzene is generated. So whenever there is benzene ring with fluorine, bromine, or fluorine, bromine, when we add magnesium or lithium, then we observe the formation of, if we take lithium, then we expect the formation of lithium, bromine replaces the lithium replaces the bromine, then we expect the benzene formation this way. Or if we use magnesium instead of lithium, fluorine, bromine, if we add magnesium to this, magnesium, lithium, these are all the strong bases. Only in the presence of strong bases we can expect the benzene formation. So we get benzene and the byproduct is MgBrF. So these are the few examples where we observe the formation of benzene. So this is the complete information about reaction intermediates in the organic chemistry. So if you find this video helpful, please like, share and subscribe. Thank you. Hello all, welcome to the channel. Today's topic is hyperconjugation. This is the fifth type in the electron displacements and also the most powerful among all the effects. Okay, so it is a phenomenon which is nothing but the delocalization of the sigma electrons of CH bond. Okay, delocalization of the sigma electrons of CH bond that are attached to a pi bond or a p orbital. The CH has to be attached to either a pi bond or a p orbital. Then we observe the sigma electrons shift or delocalization from the CH to the pi bond. Such effect is called hyperconjugation, or it is also called no bond resonance. I'll explain why it is called no bond resonance. And also it is considered to be Baker-Nathan effect. These are the different names given for hyperconjugation. hyperconjugation or Baker-Nathan effect or no bond resonance. Now, what are the conditions that we have for hyperconjugation to occur? The main and foremost condition that we have is it should have alpha carbon and alpha CH bond adjacent to either an sp2 carbon or any other atoms like nitrogen or oxygen. Let us see clearly with an example. So consider the example propene, which is CH3 CH double bond CH2. Now the main criteria or the condition for hyperconjugation is the sp2 carbon or a p orbital of either nitrogen or oxygen, etc. So here we have sp2 carbon because this carbon is sp2 double bonded, this carbon is also sp2 double bonded. Now if we split this in the form of orbital diagram, then we can write this as CH single bond CH2. Then this pi bond, we know that it is formed by the sideways overlapping of p orbital. So this is the p orbital that is formed by the overlapping sideways. So this will have one single electron, this will also have one single electron. For the representation wise, I am writing both in the upward arrow. So this is the pi bond that we can see. Now what do we have? We have an adjacent carbon. Now what do you call this carbon? The carbon that is directly attached to any functional group or a double bond, you call it alpha carbon. Now that alpha carbon has 3 hydrogens, so they are all called alpha hydrogens. So this alpha hydrogen presence will cause the hyperconjugation effect. So let us see, this is an sp3 carbon, so one will be above the plane, one will be below the plane, and the other will be on the plane. So this is the hydrogen. Now this hydrogen, carbon hydrogen bond is formed by sp3 carbon and s orbital. So it is a sp3 s orbital bond formation, that is obviously a sigma bond because hydrogen has only s orbital. So now what do we observe here is this sigma bonded electrons are going to be shifted towards this side. So sigma bonded electrons are shifted towards this side, and whatever pi bonded electrons are there, those will be shifted towards this carbon. So accordingly we can observe the formation of CHH. Now this hydrogen, since it has only 2 electrons but gave out those 2 electrons, it will be left with no electrons, so it is H plus. Now since this bond got shifted here, now this carbon will get a double bond, then again this bond is shifted towards this side, so it becomes carbon single bond with 2 hydrogens and a negative charge this way. So now again if you observe, this will repeat, this comes to this side and this will goes to this side. Again the process happens with the other 2 hydrogens also. Since hydrogen is losing its bond by giving out its 2 electrons, this is considered to be a no bond resonance. So this happens with how many ever alpha hydrogens are there beside the double bond, that many number of conjugated structures are formed. Since there are 3 alpha hydrogens here, we can expect this to be happening 3 times in propene. Similarly, if there are more alpha carbons and more alpha hydrogens, we can observe more hyperconjugation effect. Now because of the alternate carbon-carbon single bond and double bond, the bond length will vary. Bond length in case of propene is observed to be 1.48 angstroms. It is less than single bond and greater than double bond. So it is in between the two, that is 1.48 angstroms. And the bond order also will vary because sometimes it is acquiring single bond, sometimes it is acquiring double bond. So hyperconjugation can cause many changes in the molecule. Let us see the applications of hyperconjugation. Now let us see the applications of hyperconjugation, which is the most important part of this concept. Now if you find this video helpful, please like, share and subscribe and share it with your friends. Thank you. So let us see the first application, that is the stability of alkenes. So stability of alkenes can be calculated or told based on the number of alpha hydrogens, because as the number of alpha hydrogens are increasing, this is directly proportional symbol, this is alpha. So as the number of alpha hydrogens increase, the number of hyperconjugation contributing structures are going to increase. So hyperconjugation will also increase. So we have butene, that is CH3, CH2, CH double bond CH2. This is one butene, and we have two butene, that is C double bond C, CH3, CH3, this is CH and H. We need to fill the valency. Okay, this is 2 butene and that is 1 butene. So first we need to look at the double bond. So here is our double bond, we have spotted it. Now we need to look at the alpha. So whatever carbon is directly attached to the double bond, that is your alpha carbon. So here we have one alpha carbon. I'll change the color. So this is your alpha carbon, and for this double bonded system we have 2 alpha carbons. So this alpha carbon has 2 alpha hydrogens, 2 alpha hydrogens. For this it is 3 plus 3, 6 alpha hydrogen. So 2 alpha hydrogens indicate less hyperconjugation, 6 alpha hydrogens indicate more hyperconjugation. So obviously 2 butene is more stable compared to that of 1 butene. So this way hyperconjugation can be explained based on the presence of number of alpha hydrogens, and accordingly the stability can vary. So if you can see the order of different alkenes stability, then the least one will be ethylene, because it's the basic one with no hyperconjugation or alpha carbon, compared to propene. So as the substitution increases, then comes the disubstituted, then comes the disubstituted on one side and monosubstituted on the other side. Similarly we can replace this hydrogen also with one more methyl, and we get CH3 twice C double bond C CH3. This is the increasing order of stability of alkenes with the increase in the number of alpha carbons. So this is mainly supported by a factor or the property called, phenomenon called hydrogenation values or heat of hydrogenation. So it is mainly calculated according to the heat of hydrogenation. Now what is heat of hydrogenation? It is the energy that is released when we add hydrogen molecule to any unsaturated compound. So whenever you are adding hydrogen molecule to any double or triple bond, the energy that is going to be released, because it's an exothermic process, such energy is called heat of hydrogenation. And what is the relation between heat of hydrogenation and the stability of alkenes? It is inversely proportional. So whichever alkene is stable, that alkene will release less amount of energy when hydrogen is added to it. So hyperconjugation explains the stability of alkene, and also it is explained in terms of heat of hydrogenation. So we can calculate the stability as well as the heat of hydrogenation with the help of hyperconjugation. This is the first application. Now the second application is the stability of carbocation. So carbocation stability can be explained by hyperconjugation. So what is a carbocation? Let us look at the ethyl carbocation, that is CH3 CH2 plus. Okay, so here this has, methyl has 3 hydrogens, carbon with 3 hydrogens, and this carbon has 2 hydrogens, and here this positive charge indicates what? An empty p orbital. When we were talking about the condition for hyperconjugation, we said that either there has to be an sp2 carbon or an empty or p orbital in hydrogen or oxygen or any species. So here we are considering carbocation with p orbital, empty p orbital. Now what we observe here is this bonded, this is the alpha carbon with alpha hydrogens. Now this sigma bonded electrons are given onto the carbon with positive charge or empty orbital. Hence we can see the shifting of sigma bonded electrons from hydrogen onto the empty p orbital in among the 3 hydrogens. This way the positive charge in the carbocation is stabilized by 3 alpha hydrogens. So as the number of alpha hydrogens increase, the stability of carbocation also will be increased. Cation increases with the increase in the alpha hydrogens. This way, if we can see the order, methyl carbocation is less compared to primary carbocation, that is CH3 CH2 plus. Then comes the secondary, that is CH plus with 2 methyl groups, CH3 and CH3. Then comes the tertiary, that is carbocation with the 3 methyl groups. This is the increasing order of stability because of the increased hyperconjugation. This is the second application of hyperconjugation. Stability of free radicals can also be explained by hyperconjugation, as in the case of carbocations, because free radicals are also nothing but the carbon with p orbital containing single electron. So there can be again the shift of hydrogen bond from alpha carbon to the p orbital. Hence it follows the same order, like methyl carbocation is less stable compared to primary, less stable compared to tertiary and secondary and tertiary. So this is the order same as that of the carbocations. So the next application is about dipole moment and bond length. So whenever we see hyperconjugation, suppose in case of methyl nitrate, the present example, we can see the alpha hydrogen bond is shifted onto the carbon nitrogen bond, and this pi bond is shifted onto the oxygen. Accordingly we are getting CH2 H plus with no bond. Then here we are getting the double bond. Then comes single bond with O negative charge here, and the coordinate bond is remaining as it is. So here, while we are getting the second structure from the first structure, what are we observing? Single bond is turning into double bond. Here single bond is turning into double bond, then double bond is turning into single bond between nitrogen and oxygen, and the charges are developed. In the first structure there are no charges, but in the second structure there is positive and negative charge. Now because of the development of charges, dipole is created, or the polarity is created. Because of the charges, polarity is created, and the dipole moment also will vary. Because of hyperconjugation, dipole moment is varying, and also the bond length. In the first structure, different atoms were having single bond and double bond. Now different atoms are having single bond and double bond. Now because of the shift of bonds between single and double, bond lengths also vary effectively, and we can see it in the experimental values as well. So these are the 4 different applications of hyperconjugation that we have discussed in detail. Thank you. Hello all, welcome to the channel. Today's topic is electromeric effect indicated by the symbol E. Electromeric effect is nothing but the instantaneous formation of a dipole. Dipole is nothing but positive and negative charge separation. So whenever there is a multiple bond like C double bond O for example, whenever there is a multiple bond, we observe the complete transfer of pi electrons. Electromeric effect is the complete transfer of the pi electrons from one atom to the other in the multiple bond like double bond or triple bond. Only this happens when there is an attacking agent. Could be a nucleophile or an electrophile. So whenever there is an attacking agent like an electrophile or a nucleophile, then in the molecules that contain multiple bonds, we observe the complete transfer of pi electrons resulting in the formation of a dipole. Such effect is called electromeric effect. Now this effect is considered to be temporary effect because this effect disappears when we remove this attacking agent. If there is no nucleophile or electrophile, then electromeric effect is absent. It happens only in the presence of an attacking agent like electrophile or nucleophile, and this happens only in the molecules that contain multiple bond like double or triple bond containing compounds. Only in those you can observe the electromeric effect, and it is mainly of two types, same as the other effects, that is plus E effect and minus E effect. The first type is positive electromeric effect, that is plus E effect. Here plus E or minus E depends on the attacking agent. If you can see, the attacking agent here is the H plus, that is the electrophile. Electrophile is nothing but electron deficient species. So electron deficient species, what it does, it will always try to attain the electrons. So we observe the shifting of pi electrons from one carbon to the other. Accordingly, this gets the negative charge, this gets the positive charge. So obviously this negative charge will go and attack the H plus ion. That results in the formation of hydrogen attacking at the second carbon. This is the positive electromeric effect that is created because of the electrophile, and this will disappear. It will remain as it is after the removal of H plus ion. The second type is the negative electromeric effect, that is the minus E effect, where the attacking reagent here is the Cn minus, that is electron rich species, that is the nucleophile. Nucleophile is nucleus loving. So we observe the shift of pi electrons from one carbon to the other. Accordingly, this gets the negative charge and this gets the positive charge. So Cn minus is already electron rich, so what it will do, it will attack the positive part of the double bonded molecule. Hence we can see the Cn attacking the first carbon and second carbon remains negative. Now this is left for any electrophile to attack. It can be H plus generally. So such effect is called negative electromeric effect, and this again disappears when there is no attacking reagent like nucleophile. So these are the this is the weak and temporary effect that we can see in the molecules with double bond or triple bond, and only it happens in the presence of attacking reagent. So these are the two types of effects in electromeric, plus E and minus E. Hello all, welcome to the channel. Today's topic is about the resonance effect. It can be either plus or minus R effect. Resonance is nothing but the shift of pi electrons or the displacement of pi electrons from one atom to the other in a given molecule. So this shift of pi electrons happens in an alternate system, that is the resonance phenomenon. Now based on the direction of this shift, whether it is going towards the ring or away from the ring or towards the molecule or away from the molecule, accordingly we'll have plus R or minus R effect. Let us see clearly with two different examples. First is aniline. Aniline is benzene with NH2. Okay, now here NH2 group is considered to be the plus R group because of the lone pair on the nitrogen. It is acting as an electron releasing group. Now what does an electron releasing group do? It will transfer the electrons from its lone. The lone pair is transferred from nitrogen onto the benzene ring, and since the benzene ring has alternate pi electrons, as you can see here, 1, 2, 3. There are 3 pi electrons present in the pi bonds present in the benzene ring. So we see alternate shifting of pi electrons. Now this results in the formation of various resonance structures that results in the formation of negative charge on the benzene ring and positive charge on the group that is attached to the benzene ring. So hence such effect is considered to be the plus R effect, and the resonance hybrid is considered to be the benzene ring with a circle inside and NH2 group on the top. This is the resonance hybrid, which is the most stable form. Okay. Now while donating electrons, amine is creating negative charge at two different positions. We consider the adjacent position for the carbon attached to NH2 is considered to be ortho position, and the 1,3 position is considered to be meta, and 1,4 position is considered to be para. So since while donating electrons, amine is creating negative charge only at ortho and para positions. If you can see in the second, third and fourth structures, only ortho and para positions are getting the negative charge. So what happens? This results in the attack of an electrophile only at ortho and para positions. So NH2 or plus R groups are also called OP directing groups or electron releasing groups. So whenever you add any electrophile onto the plus R groups or the aniline molecule, we can expect the electrophile attack only at OP position and not at the meta position. What is ortho position? This is the first carbon that is attached to NH2. This is the second carbon, third, fourth, fifth and sixth. So 1, 2 position is called ortho, and 1, 4 position is called para, and 1, 3 position is called meta. So these are the 3 different positions, and negative charge is developed only at ortho and para positions. Similarly, let us look at the minus R effect with nitrobenzene example. So nitrobenzene is nothing but benzene ring with NO2 group. So NO2 group is considered to be the strong electron withdrawing group because of the greater electronegativity of the atoms present in it. So what happens? The pi electrons are pulled towards oxygen, so nitrogen gets positive charge. Positive charge on more electronegative atom like nitrogen is unstable. So what happens? This pi electrons are pulled towards the nitrogen. So hence we are going to get various structures like this: 1, 2, 3, 4, 5. So as we can see, the electrons from the ring are moving towards the group that is attached to the benzene ring. Such effect is called minus R effect, and accordingly on the benzene ring we observe positive charge, and positive charge is observed at which positions? Ortho and para positions again. These are called electron withdrawing groups or minus R groups, or OP non-directing groups also we can call them. So such effect is considered to be the minus R effect. Now let us look at the order of species that are showing the resonance or mesomeric effect. Okay, so like we have seen in the case of inductive effect, the examples were like according to the electronegativity, but here it's a bit different. So minus R effect is shown mainly by nitro group, followed by cyano, followed by ketone, followed by aldehyde, acid and acid substituted acids, or we can say ester. So plus R effect is shown by chloro, bromo, iodo, amine, NH substituted amines. Then we have amides, alcohol, ether, substituted substituted thiol, methoxy and esters. So this is the order of plus R effect shown by these groups in different molecules. Similarly, minus R effect is shown in this order. So whenever, if you remember this order, you will be able to find out which molecule will have greater plus R effect and which molecule will have least minus R or least greater minus R effect. If you find this video helpful, please like, share and subscribe, and tell your friends and come back to this channel. If you need anything, any such videos, comment in the comment box. Thank you. Hello all, welcome to the channel. Today's video is about the rules of resonance. So in the previous video we have seen what is a resonance phenomenon. If you haven't checked out the video, I'll give the link in the description box. Just go check it out before coming to the rules of resonance. So why do you have to know the rules of resonance? So if you have to write the resonance structures, we need to know if those resonance structures are valid or not. So these resonance structures should be valid only if they follow the octet rule. Resonance structures or the Lewis forms that you write should follow the octet rule. For example, if you consider methyl nitrate CH3N double bond O, NO2. If we write it in the neutral form, we write with a coordinate covalent bond, but since we need to look at the Lewis structures, we do not write the coordinate covalent bond, we just write the charges on both the nitrogen and oxygen. So overall this molecule is non-neutral because plus and minus charge are equal and they get cancelled with each other. Now this is the first form of Lewis structure. So we need to see if this molecule is stable and it follows the octet rule or not. Okay, so here all the atoms that we consider should follow the octet rule. That means carbon should have only 4, nitrogen cannot have 5 bonds. Nitrogen here it has 1, 2, 3 and 4 bonds. Maximum bonds that the nitrogen can have only is 4. So the first structure is valid. Now the second canonical form of this structure could be CH3NO double bond O. Now what happens is this negative charge will shift towards this side and this charge shift towards this side. So that results in CH3N double bond O minus plus on nitrogen. So we are observing only the shift of pi electrons and the shift of negative and positive charges. So positive charge all the time it is on nitrogen, negative charge is shifted among the first and second oxygens only. So these two are the valid canonical forms for the methyl nitrate. Suppose if we write it in this form CH3N double bond O and double bond O. If we write it in this way, though this structure has no charges, this is considered to be an invalid resonance structure because nitrogen valency here it is 5. So nitrogen can never have 5 valency because it lacks the d orbital in it. So Nitrogen cannot have 5 valency. Now this structure is not following the octet rule, so hence it is not valid. So the first rule for the resonance structures is they should follow the octet rule. And what is the second rule? All the atoms should possess same number of electrons, and also they should have equal net charge. If you can look at the above first and second examples, both have 1 plus and 1 minus charges, so the net charge is same, and they have same number of electrons around each atom. Okay, this is the second rule that each canonical form should have. And also they should have same number of paired and unpaired electrons. Paired electrons are nothing but bonded electrons. Unpaired electrons are nothing but the lone pair of electrons. So that they are also the same. So hence these two structures are considered to be the proper and valid resonance structures. Okay, the next rule or the fourth rule is position of atoms in the two resonance structures should be the same. Position of atoms in the two canonical structures should be the same. If you look at this above example, here we have CH3, CH3, C double bond O. This is considered to be ketone. And here it is CH3COH double bond CH2. This is enol form. So the position of hydrogen here, it is with oxygen, now here it is with hydrogen. So since the position of hydrogen is changing, now these two are considered as not resonance structures. They are considered to be the tautomers. They are tautomers but not the resonance forms. So in the canonical or resonance structures, the bond connectivity can be different. The bond connectivity has to be same, but the bond order might change from one atom to the other, and the resonance structures may not be equivalent also. Bond order may change and the resonance structures may not be equivalent sometimes, but we always see to that all the atoms in the plane are on the same plane, so that maximum overlapping takes place. Maximum overlapping of orbital leads to more stability of the molecule. Now let us see the rules to decide which resonance form will contribute more to the resonance hybrid. So whichever resonance form is more stable, that is going to contribute to the resonance hybrid. Now if you look at the first structure has the contributing structures that have full octet are more stable. So look at the first one. Carbon has only 3 bonds, 1, 2, 3. That means it has only 6 electrons. But here in the second structure, carbon has 1, 2, 3, 4 bonds. 4 bonds means complete octet. So hence second structure is more stable and all the atoms are having the octet, more number of covalent bonds compared to the first form where carbon has only 6 electrons, which is sextet, and here it has full octet configuration. So the second form is more stable. And the resonance structures with few charges on it are more stable compared to those which have more charges. If you can look at the second example, here in the first form there is only one charge on oxygen, that too electronegative atom with negative charge is a bit more stable compared to the electronegative atom with positive charge. Of course in this case, in both the structures, electronegative atoms have negative charges. So here in the first form there is only one negative charge, but in the second form there are 2 negative charges and a positive charge. If at all the positive and negative charge gets cancelled, the overall charge is negative. So the charge on both the cases, it is the same. Both are getting the net negative charge same. But the second form is less stable compared to the first form, and the second form is considered to be invalid. It is because on a single structure, if there are two negative charges, 1 and 2 negative charges, it makes the molecule more unstable. Though the overall charge is the same, since it is getting two negative charges on a single molecule, that too such a small molecule, this results in the instability of the molecule. So hence the molecule or the structure that has full octet will have more stability, and also with few charges will have more stability. Hello all, welcome to the channel. In the previous video we have seen what is inductive effect and the types, and in today's video let us see the phenomenon called resonance. Before going into the resonance effect, we need to know what is resonance. So let us see this phenomenon first. So the example that is in front of you is the benzene structure. Benzene is the best example to explain the resonance phenomenon. We have other molecules also which shows resonance, but here we are considering benzene. So what is the phenomenon called resonance? The phenomenon of resonance is nothing but the molecule, the given molecule like benzene, if it is not able to written in a single form, you cannot write it in one form to explain all its properties, but you write it in multiple forms. As you can see, there are 5 forms for benzene. Okay, so when a molecule can be written in 2 or more forms, such phenomenon is called resonance. So how can you write resonance structures? You need to keep the basic structure the same. It should have 6 carbons linked one after the other, and the carbon skeleton has to be the same, but only what differs is the distribution of electrons will vary from one structure to the other, and the charges vary on one atom to the other. Only the electron distribution and the charges will differ, but the carbon skeleton is going to remain the same. So in one structure, if it is C6H6, in other structure it cannot be C6H5 or something else. So this is wrong. So in resonance, we write a structure, a molecule in various forms where the distribution of electron and the charges will vary, but the carbon skeleton remains the same. This is the phenomenon called resonance. Now, what are all these structures called? The main 2 structures, these are the structures given by Kekule. They are called Kekule structure. They are the most stable forms of benzene, and the remaining 3 are called Deva structures. Deva structures are not so famous because they do not give clarity about all the properties of benzene, but the Kekule forms are the most stable forms. So here, these are all forms are considered to be the canonical forms or the resonance structures. The various structures that we write for a compound in resonance are called canonical forms or the resonance structures. The mixture of all these forms that we write is considered to be the resonance hybrid. What is it? It is the resonance hybrid. We write it this way. This circle inside the benzene ring indicates the distribution of pi electrons throughout all the 6 carbons. This is known as resonance hybrid. Resonance hybrid is the most stable form of the structure which follows all the characteristics. So when we say the resonance hybrid is more stable compared to the canonical forms, it's in terms of energy. So the energy of resonance hybrid is very less compared to that of the remaining canonical forms. This difference in energy is called resonance energy. What is resonance energy? The energy gap that we see between all the canonical forms and the resonance hybrid, that is this form. So this is having the least energy. We know that energy and stability are inversely proportional. So hence resonance hybrid has the least energy and most stable form. So among all the structures, the resonance hybrid that we see here follows all the properties of benzene or the bond parameters, like the carbon CC bond here is not completely single and it is not completely double. It is in between. It is like this. That means all the carbon atoms, they experience single bond sometimes and double bond sometimes because of the delocalization of the pi electrons. Hence the carbon-carbon double bond in the benzene experiences the bond length in between single bond and double bond, which is 1.39 angstroms. For single bond it is 1.54 angstroms. For double bond it is 1.20 angstroms, but for benzene it is in between, less than single bond, greater than double bond, that is 1.39 angstroms. And the resonance energy or the energy gap that we experience between the resonance hybrid and the canonical forms is 36 kilocalories of energy. Now because of this resonance energy, benzene hybrid is more stable and it helps in its reactivity also, like it undergoes reactions in electrophilic substitution reactions. Benzene, because of this extra resonance energy that it possesses, it participates in the electrophilic substitution reactions. This is the phenomena of resonance with the help of benzene molecule. Thank you. If you find the video helpful, please like, share and subscribe. Hello all, welcome to the channel. Today's topic is types of inductive effect. In the last video we have seen already what is inductive effect. A quick glance of it, let us see. So inductive effect is nothing but the shifting of sigma bonded electrons from a less electronegative element to the more electronegative element. So it is of mainly two types, minus I effect and plus I effect. Okay, so whenever you see an electronegative atom connected to the carbon chain, we observe minus I effect, and an electropositive group like the methyl group connected to the carbon chain, we observe plus I effect. So here's an example. Here we have CH3NH2, where carbon and nitrogen electronegativity difference is very large. So obviously nitrogen is going to pull the electrons towards it, leaving carbon with positive charge and nitrogen with partial negative charge. Such effect is called minus I effect. Whereas methyl group also contains carbon and the carbon chain also contains the carbon. So here the methyl group, what it does, it will donate the electrons onto the carbon chain. Accordingly, carbon chain gets the negative charge and the methyl group gets the positive charge. This results in the plus I effect. So we need to only look at the group attached to the carbon chain. So what is the symbol? This is delta, which indicates the partial positive and partial negative charge. So this inductive effect is a permanent effect and it stays only within 3 to 4 atoms. So if you can see this example, it started with nitrogen and it lasts only up to first, second and third carbon. As we go far away from the chain, the effect becomes very, very less. Similarly, the negative effect also happens in the same way. But this is a permanent effect in the molecules. It is a permanent effect but weaker effect. So let us see the groups that create minus I effect and the groups that create the plus I effect in different molecules. So nitrogen being the most electronegative in combination with oxygen and other elements. So let us see the tri-substituted ammonium. NR3 is the most strong minus I group. Then comes the nitro, then comes the sulfate substituted SO2, then you have cyano, acid, fluorine, chlorine, bromine, iodine are the weak minus I groups. Then you have substituted alcohols, then you have substituted ketone, alcohol, phenyl, vinyl and least is the hydrogen. Similarly, we have plus I groups where the carbon with the more substituted methyl groups, that is trimethyl substituted carbon is the strong plus I group. Then comes the disubstituted, then comes the monosubstituted, then comes methyl, then deuterium, then in the least you have hydrogen. Hydrogen shows least minus I effect and the least plus I effect. These are the few examples where we can estimate which molecule can have stronger minus I effect in the molecule and which molecule can have stronger plus I effect in the molecule. So the effects that are caused by the plus I groups and minus I groups is mainly acidity, basicity, carbocation stability and carbanion stability. So the plus I groups are going to decrease the acidity of the molecule and minus I groups are going to increase the acidity of the molecule. Similarly, plus I groups are going to increase the basicity of the molecule and minus I groups are going to decrease the basicity of the molecule, because plus I groups are electron releasing and minus I groups are electron withdrawing groups. Okay, so carbocation is nothing but carbon with the positive charge. So it already has a positive charge. Whenever there is a group that donates the electrons, like plus I group, is going to increase the stability of the carbocation. The carbanion is nothing but carbon with a negative charge. Whenever there is a group that pulls the electrons towards it, like minus I group, it's going to increase the stability of the carbanion. So hence, carbocation stability is increased by plus I groups and decreased by minus I groups. Carbanion stability is decreased by plus I groups and increased by minus I groups. So these are the four most important features that are going to be affected in a molecule that possesses either plus I effect or